Okay, this is 2016 first structured essay. 2016 K level first structured essay. First structured essay under Unit 2. Unit 2 and the first question A part is also related to inorganic. Inorganic also related. Unit 6. Inorganic is also related. Okay. So the question 1 A part, you are provided with the following list of some p block elements in the periodic table. From the list, identify the non-metallic element that forms an homoatomic covalent lattice of high hardness. Now, what forms this covalent lattice? Group 4 elements, right? Carbon, silicon, germanium. Okay. In our syllabus, we have carbon and silicon. We are going to study about this in fourth group. We are studying about this carbon and silicon. So, if you therefore you can take carbon and silicon as the answer. But you see what they have asked. They have asked identify the non-metallic element. So from this carbon and silicon, which is non-metallic, carbon is the non-metal. Then what is the silicon? Silicon is metalloid. Silicon is metalloid. Therefore, carbon should be the answer. Carbon should be the answer. Therefore, answer is carbon. Check the B part. Sorry, not the B part. This is Roman number 1 and then Roman number 2. Identify the element that has the highest first ionization energy. Now, what is the order of this first ionization energy? First ionization energy. Across a period, what happens to first ionization energy? IE1 increases. And also, down a group, what happens to first ionization energy? IE1 decreases. First ionization energy decreases down the group. Across a period, first ionization energy increases. Down the group, first ionization energy decreases. Therefore, across a period, if first ionization energy increases, therefore, it's for sure noble gas should be the answers. Noble gas should be the answers. From that also, it said that the down the group, ionization energy decreases. No? Therefore, one with the highest first ionization energy should be at the upper level in the group. It should be in the upper level in the group. Therefore, answer is neon, right? Answer is neon. Neon and argon, no. Neon is a top, is at upper level in the group, no. From along the group 18, neon is upper to this argon. Therefore, neon should be the answer. This is Roman number 3, no. Sorry, this is Roman number 3. Therefore, what's the answer? Neon is the answer. Now, let's see Roman number 2. Identify the element that exhibits the widest range of oxidation states. In our syllabus, what is there? Now we can take this nitrogen. Nitrogen, what is the range of oxidation number? Range is from -3 to +5. For nitrogen, -3 to +5. Then what we have? Boron we can't take. Carbon we can't take. Oxygen also there is -1, 0. Yeah, -1, 0, O2, O3. -2, -1, 0. Therefore, we can't take there. There is only 3. Then fluorine also we can't take. In nitrogen you can take. Other than that, chlorine you can take. Chlorine, what is the range? from -1 to +7, like chlorine -1 to +7. And then what else you can take? Sulfur. Sulfur also you can take. What is the range of sulfur? -2 to +6. Therefore, these three you can take as the answer: nitrogen, chlorine, and sulfur. Nitrogen, chlorine, and sulfur you can take as the answer. Yes, this for Roman number 2. This, or this. Then Roman number 4. I'm going to clean this. Then Roman number 5. Roman number 2 done, 3 done. Then Roman number 4. Roman number 4. Identify the element that exhibits amphoteric properties. So, what are the elements? It should be either aluminium or beryllium. Why this aluminium and beryllium? Now, if you take the periodic table, helium, okay, because of the diagonal relationship, we can say that the aluminium and beryllium are amphoteric. What is this diagonal relationship? Here, beryllium and aluminium, they have diagonal relationship between each other. Therefore, we can take the aluminium and beryllium are amphoteric. And also there is another diagonal relationship, not related to this question, but I'm just lithium and magnesium. And what is the proof that both of these show the amphoteric properties? Sorry, what is the proof to say that they have this diagonal relationship? You know, in the first group, lithium is the only element which react with nitrogen to form lithium nitrate. And this magnesium is also react with nitrogen to form this magnesium nitrate. That is a proof to say that lithium and magnesium have diagonal relationship between each other. Aluminum and beryllium is also have diagonal relationship. What is the proof to say? The amphoteric properties between them. That's it. But here beryllium is not given. Therefore, answer should be aluminum. Answer should be aluminum. This is Roman number 4. Then Roman number 5. Identify the element that has two gaseous allotropes. You know it's oxygen, right? Oxygen has two allotropes, O2 and then O3. Oxygen and ozone. These are gases. In the atmosphere, these are gases. Therefore, element that has two gaseous allotropes is oxygen. Answer is oxygen. Roman number 4 done. Roman number 5 done. Then Roman number 6. Identify the element that is considered to be the strongest oxidizing agent, that is fluorine. Fluorine is the strongest oxidizing agent. What is this oxidizing agent means? Oxidizing agent will reduce, right? Oxidizing agent will reduce. Now, how this oxidation of fluorine occurs? Fluorine from F2 fluorine, that is zero oxidation state, will be reduced to F minus, that is -1 oxidation state. Therefore, F2 is the strongest oxidizing agent. Down the group, what happened? Down the group 17, the oxidizing ability of halogens decreases. Down the group, oxidizing ability of halogens decreases. Decreases down the group. Oxidizing ability of halogens decreases down the group. Therefore, strongest oxidizing agent is fluorine. Answer should be fluorine. That's it. A part is done. Now we'll move to B part. Now we'll move to B part. B part. The following part 1 to 5 are based on the molecule CN4. It has the following skeleton. Assuming that N bond lengths are approximately equal, draw the most acceptable Levy structure for this molecule. So what is the skeleton given? This is the skeleton. N, C, N, N, N. This is a skeleton. Draw the most acceptable Levy structure for this molecule, and also they have said, assume that N bond lengths are equal. This bond length and this bond length should be equal. Okay. Now count the number of valence electron. In nitrogen, how many valence electron? 5. This nitrogen, nitrogen 5 and carbon 4. No. 5, 10, 15, 20, 20 plus 4, 24. Therefore, there are 24 valence electrons. Okay. Then how many bonded electrons are there? 1, 2, 3, 4, 5, 6, 7, 8. Therefore, from 24, subtract 8, you will get 60. Okay. Now, these are the number of electrons. No, these are number of electrons. Then how many pairs are there? How many pairs are there? You should divide by 2. Then you will get 8 pairs of electrons. 8 pairs of electrons. 8 pairs of electrons. First of all, what you should do, these electrons should be distributed to the not to the central atoms, but to the terminal atoms. You should distribute this pair of electrons to the terminal atoms. Okay. Therefore, there are 8 pairs now. 1, 2, 3, 4, 5, 6, 7, 8. You can distribute these both the electron pairs to one nitrogen or else to both the nitrogen. I will distribute to both the nitrogen. Okay. Just we are going to check it now whether the structure is going to be stable or not. You can give to either for one or for both. Okay. Clean this. Now what you should do to complete the octet, you should get the electrons from the terminal atoms. Now here you see in nitrogen, the octet is not completed. Only 6 electrons are there. Therefore, this nitrogen, this lone pair should be converted to bond pair. So here we have, okay. And then in this nitrogen also, there are only 6 electrons around in there. To make it, to make the octet complete, I'm going to make this lone pair as bond pair. So I'm going to do this. Okay. And then in this carbon also, in this carbon, only 4 electrons are there surrounding it. To make it octet, I'm going to take 2 lone pairs from this. I'm going to take this and this. Okay. Therefore, what's going to happen? 2 bonds are going to form. 2 bonds are going to form. Now, let me assign the formal charges for this. Here, 1, 2, 3, 4, 5, 6. How many valence electrons that should be to this nitrogen? 5, no? But it has 6 electrons. There is extra 1 electron, therefore assign a negative charge. Here, 1, 2, 3, 4. It should have 5, it has only 4, then 1 electron is lost, therefore plus charge. Here 1, 2, 3, 4, 5, no formal charge. Here 1, 2, 3, 4. Carbon should have 4 valence electron. There is 4 valence electrons surrounding it, therefore no formal charge. Here also 1, 2, 3, 4, 5. Yeah, no formal charge. This is the stable structure. This is the stable structure. Now, for example, now I have taken, now initially there were 2 lone pairs to this nitrogen. I have taken both the lone pairs and make bond pairs to make this carbon octet. Now what will I do? I'm going to take one night. Now this is the stable structure. This is the stable structure. And you will have doubts why the other structures are not stable. Now let me see. Now I have taken both the lone pairs and make this bond pair. Now I will remove one pair and I will give to it. And then remaining pair. Now this for this carbon, octet is not complete. I can take the lone pair from this nitrogen or else from this nitrogen. This nitrogen also have a lone pair. I will take from this. Okay. Now we'll see. If I take like this, now let me assign formal charges. 1, 2, 3, 4, 5, 6. Because it should have 5 valence electron, but it has 6 valence electron. There is an extra electron, therefore negative charge. Here no formal charge. Here 5 should be 5 is the valence electron, but it has only 4 valence electron, therefore it should have positive. Is this a stable structure? No, it's not a stable structure. Why is that? Because in a resonance structure, if the two adjacent atoms have the same charge, either positive positive or negative negative, then it is an unstable structure. Then it is an unstable structure. Okay, it is not a stable structure. But earlier structure, you see what has happened. Here, I have taken the lone pair from this nitrogen, taken from this nitrogen. Here, 1, 2, 3, 4, 5, no formal charge. Yeah, this had the lone pair initially, no formal charge. But if there is opposite charges on adjacent atom, that structure is stable. If same charges on it, it's unstable. Therefore, I can take this as a stable structure. Okay. And also, you might have some other doubts like why you distribute the lone pair to 2 different nitrogen atoms. I can distribute to single nitrogen. No? So yeah, let's check it. Here, I have drawn the stable structure. Initially, I have drawn the stable structure. Now I'm going to show why the other structures are not stable structures. Here, yeah, let me draw the skeleton. Then nitrogen, carbon, nitrogen, nitrogen, nitrogen. So I have calculated here how many valence electrons were there. 8 pairs were there. 8 pairs, no. 1, 2, 3. 1, sorry, 3, 4, 5, 6, 7, 8, no. Okay. Now we'll see. For this nitrogen, octet is not completed. Let me take 2 lone pairs from this and this. I have make the lone pairs as bond pairs. Lone pairs, lone pairs. Now the octet is complete. Here also the octet is complete. Here the octet is not complete. Let me take 2 lone pairs and give to this. Now let me assign the formal charge. Octet is complete now. Now assign the formal charge. Here no formal charge. Here plus, right? I'm just putting in there. Here it should have 5, but it has 4. Therefore plus. Here minus. Here 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. No. Here 4, no formal charge. Here also no formal charge. Yeah, that's it. So why is this not a stable structure? Now, in case of nitrogen, the structure will be stable when this nitrogen has this sort of a structure. It should have 1 lone pair and it should have 3 bond pairs. For nitrogen, it should, if the structure, if the for this nitrogen, if the structure If this nitrogen has this sort of a structure, one lone pair and three bond pairs, then it is a stable structure. Now, for example, for oxygen, what is the most stable structure? Two lone pairs and two bond pairs should be there. That is for oxygen. In case of fluorine, it should have three lone pairs and one bond pairs. Likewise, now, now why is this like this? You could have studied that in theory, but that is in theory. Therefore, the structure is more stable when the nitrogen has this sort of a structure. Here you see the nitrogen has this sort of a structure. But here you see nitrogen doesn't have this sort of a structure. Therefore, this is unstable. Likewise, we can say now in the next question, they have asked what's the draw the all the three resonance structures. No. Now, when we are drawing the resonance structures, I will tell you why those structures are not stable. Okay, for nitrogen, it should have this sort of structure to make it stable. Therefore, this is the most stable structure. I'm going to clean this. Okay, and now this is a stable structure. Now that's done. Roman number 1 done. Now Roman number 2. Draw three resonance structures for this molecule, excluding the structure drawn in part 1 above. Now, how to draw resonance structures? What I can do? I have drawn initially here. I can make this bond pair as lone pair and this lone pair as bond pair. It could be one structure. Okay, let me draw this. Okay, right? Okay, this is one structure. What else I can do? Hmm, yeah, I can do right. I can make this lone pair as bond pair and this bond pair as lone pair. I can do like that, no? So there is another structure. It is a useful to resonance structures. Bond pair one, the lone pair should be converted to bond pair, and one of the bond pair should be converted to lone pair. The ways of how to doing you must have studied in theory. Sorry. Alright. 1, 2, 3, 4, 5. 1, 2 plus minus. Okay. That is another structure. Now this is when lone pairs are distributed between the two lone pairs now. Now let me draw the structure. Let me draw the skeleton. Now, from this I can draw another structure. Here, check it. Here this carbon has obtained bond pair from this nitrogen. I can give both the bond pair to this nitrogen and both the lone pair to this. I can do like that, right? Okay. Make sure when you are drawing resonance structures, the octet should be completed. Yeah. For 1, 2, 3, 4, 5, 6, 7. No? Therefore, -2. Okay, right? Therefore, three resonance structures done. We have done three resonance structures. Likewise, we can do it for this one also, right? Here, I can make the two lone pairs, and I can make the bond pairs to these lone pairs. Here, when you are drawing resonance structures, you should to separate two resonance structures, you should show with this double arrow. Now you will be in your full scale paper, you will be writing this way, right? The horizontal way, right? I have drawn in the vertical direction. Therefore, when you are drawing, you should separate. To separate it, you should show with this double arrow. Now here I have drawn this vertical now, so I will show it like this. And yeah, as I said here, I can draw another one. I can make these two lone pairs as bond pairs and these two bond pairs as lone pairs. Let me draw it. Here -2, -2, here plus, here plus. Okay, right? Yeah, we have drawn 4. And also another one can be done that you tried. You can draw another one. Right. Okay. So this is how you should do converting bond pair to lone pair to bond pair. Likewise, you can do distance structure. So Roman number 2 is done. Now we are going to Roman number 3. Okay, I forgot the structures. Roman number 3. Check this. This is a stable structure which I have drawn initially. Based on the Lewis structure drawn in one above, state the following regarding the carbon and nitrogen atoms given in the table. VS-EPR pairs around the atom, electron pair geometry around the atom, shape around the atom, hybridization of the atom. Now is carbon, carbon, nitrogen N2 and N3. Here is the carbon. What is N2? This is 2. This is 2. And what is 3? That is 2. Let me put it up. This is 2. This is 3. This is 4. That is how they have named it. So what they have asked, they have asked the PSEPR pair and electron pair geometry, shape, then the hybridization. Okay. Carbon, what is the total number of VSEPR pair? What is this VSEPR pair? The sum of lone pair and the sigma bond pair. Sum of sigma bond and the lone pair. That is what is VSEPR pair. So what is this VSEPR pair? Sigma bond plus lone pair. Lone pair. So around carbon, how many VSEPR pairs are there? Two VSE, sorry. Yeah, in carbon, how many sigma bonds? One, two. How many pi bonds? Two pi bonds. We are not taking pi bonds under VSEPR pair. VSEPR pair is the sum of the number of sigma bond plus the number of lone pair. Here, for this carbon, no lone pair. How many sigma bond? Two sigma bond. So how many VSEPR pair? Two VSEPR pair. Two VSEPR pair. So what is the electron pair geometry? If 2 means what is the electron pair geometry? It is linear. Linear. What is the shape? Shape is the same as the electron pair geometry. Now, when there is no lone pair to that carbon or to any element, when there is no any lone pair, electron pair geometry is the shape. Electron pair geometry is the shape. Now, for this carbon, no lone pair, no. It has only sigma bond. Therefore, electron pair geometry is the shape. It is also linear. What is hybridization? How many VSEPR pair? Two VSEPR pair. Therefore, SP hybridization. N2, how many VSEPR pair? Is N2 no? Here, one sigma bond, another sigma bond, and one lone pair. So how many VSEPR pair? Three VSEPR pair. We don't take this lone pair. That is not a sigma bond. That is a pi bond. So what's the electron pair geometry? Should be trigonal planar. Trigonal planar. So what is the electron pair geometry? Sorry, electron pair geometry is trigonal planar. Here you consider there is lone pair. Now this is like this, no? If nitrogen is trigonal planar, it is like this, no? Now, when we are taking the shape, one should be omitted. So now what's the shape? It has an angular shape. It has an angular shape. It has an angular shape. So angular shape or V shape. You can take as angular or V. What is the hybridization? sp2, right? Because 3 VSE pair, they are sp2. And N3, how many VSE pair? It has no lone pair, only sigma bond. How many sigma bond? Two sigma bond. How many pi bond? Two pi bond. Because it has two sigma bond, then it has two VSE pair. So what's the electron pair geometry? That is linear. What is the shape? Because no lone pair, shape is same as the electron pair geometry. What is the hybridization? 1, 2. 2 VSE pair, sp hybrid. Okay, that's it. Roman number 3 done. Now Roman number 4. See the Roman number 4. In the Lewis structure drawn in part 1 above, indicate whether N2 or N3 has the high electronegativity. Give reasons for your choice. Number of atoms is as in part 3. Now, the electronegativity between N2 and N3. N2 and N3. There is a certain order that you have to check. First one, hybridization. If hybridization same, next is charge. If charge is same, then the oxidation number. Okay. If that is also same, nature of the atoms bonded to it. Nature of atoms bonded. Nature of atoms bonded. Now we'll see the hybridization of N2 and N3. You see here, what is the hybridization of N2? 1, 2, 3, right? It is sp2 hybridization. And what is the hybridization of N3? That is 1 to sp hybridization. When now how can you say the electronegativity between N2 and N3 based on the hybridization? Now, when percentage S character increases, electronegativity increases. Here you see what is the percentage of S character? Here it is 50%. Here what is the percentage of S character? Approximately 33.33%. Okay. So among N2 and N3, which has the highest percentage S character? N3 has the highest percentage S character. Therefore, N3 should have highest electronegativity. Now you have checked with this, no? That's it. If you give only this reason, you'll get the marks. Now, no need to check all these things. If you are done with the first step, if you have got the answer, then no need to check, go on. You don't need to go on. But for hybrid, if the hybridization is same, then the charge. If charge is same, then the oxidation number. If oxidation number is same, then the nature of the atoms contact weight. Now this should be the answer. So check the answer given in the marking scheme and write it down. This is the explanation. You see what they have given. N3 has higher electronegativity than N2. Based on the S character, if we see, N2 is sp2 hybridized. Yeah, the electronegativity of N3 is greater than N2 because the percentage S character of N3 is greater than N2. That's it. The percentage S character of N3 is higher than the percentage of S character of N2. Or else you can give the answer based on the oxidation. But here hybridization is mostly because you got the answer now. From this you can give it. Yeah, that's it. So Roman number 4 done. Then Roman number 5. Roman number 5. Identify the atomic or hybrid orbitals involved in the formation of following sigma bond in the Lewis structure drawn in part 1 above. Numbering of atoms is as in part 3. N1 and carbon. Now, what is N1 here? Is N1 here? They are asking the sigma bond, not the pi bond. With this nitrogen and carbon, there is a sigma bond. And what is the orbitals involved to form this sigma bond? Sigma bond. What is it? We know the atomic and the hybrid orbitals are involving in forming of sigma bond, right? Hybrid orbitals are involving in forming of sigma. Therefore, what is the hybrid orbital of N1? What is the hybridization of nitrogen? One lone pair and one sigma bond. Therefore, it is sp hybridized, right? Between N1 and carbon. What is sp hybrid orbital of N1 and nitrogen and the carbon? What is hybridization? 1, 2, right? 2 VSC pair. Therefore, it is also sp hybrid. Hybrid orbitals are involving the formation of sigma. Now, this nitrogen is a terminal atom. Therefore, you can give the atomic orbital, not the hybrid orbital. You can give the answer as atomic orbital also. So, if atomic orbital in nitrogen is formed, what should be the atomic orbital? That is 2p, right? 2p. Nitrogen. Okay. This Therefore, this lone pair is involving in the lone pair, the lone electron will form the sigma bond with this carbon. That is 2p orbital. 2p orbital. Okay, that's done. Then CnN2. CnN2. Carbon and N2. Carbon, what is the hybrid sp, no? Then what is N2? 1, 2, 3. That is sp2 hybrid orbital. sp2 hybrid orbital. sp and sp2 hybrid orbital. Then N2 and N3. N2 and N3. What is the hybrid? sp2 hybrid orbital and N3. 1, 2. sp hybrid orbital. sp hybrid orbital. Next one, N3 and N4. N3 and N4. Now, what is the orbital? N3 and N4, right? What is the hybrid? 1, 2. That is sp hybrid orbital. And N4, 1, 2, 3. 3 VSEPR pair. Therefore, sp2 hybrid orbital. sp2 hybrid orbital. Because this is a terminal term, you can give as 2p also. Instead of sp2 hybrid orbital, you can give 2p atomic orbital. 2p atomic orbital. Okay, that's the answer. Therefore, B part is also done. A part done, B part done. Now the C part. Now the C part. SF6 and OF6 are both stable molecule. No, it's wrong. SF6 is a stable molecule, but OF6 is not a stable molecule. Why is that? Because this sulfur can form bonds. It can form more than 4 bonds. It can have it can The octet rule is not valid for this sulfur. Why is that? Because this sulfur belongs to third period. Therefore, it has D block. Sorry, it is because in the third period, they have D atomic orbitals are also there. D orbitals are also there. Because it has D orbitals, the electrons will get under promotion and then they can form more than 4 pair. They can form more than 4 bonds. But in case of oxygen, there is no D orbital. There is no D orbital. Only S and P orbitals are there. Due to absence of D orbital, it cannot, it should complete the octet. The octet rule is valid for this. It should have only 4 bonds around it. But for SF6, it's okay. that if you draw all the boxes and you can see sulfur, the electronic configuration. If you write the electronic configuration and if you put all this in C, then you can see that due to this promotion, the bond pairs will get promoted and it will fill up these d orbitals, and then it can form further bonds. It can form more than 4 bonds. Yeah. So, false. Roman number one is false. Now we'll go to Roman number two. In Roman number two, although the electron pair geometry of SiCl4, NCl3, and SCl2 is tetrahedral, their bond angles are different. Now, what is the now? Let me draw the SiCl4. If you draw it, you will get the answer NCl3, and then SCl2. So, what is the electron pair geometry in all of this? That is tetrahedral, right? Tetrahedral. Although the electron pair geometry is tetrahedral, their bond angles are different. Yes. Now, what is the bond angle here? Here, bond angle is 109.5 degree. Here you can see, due to lone pair bond pair repulsion, what will happen to this bond? The angle will reduce. If the angle reduces, then the theta should be less than 109.5 degree. Here also, it will have this sort of a shape. It is not 109.5 degree. Lone pair, bond pair repulsions are there. Therefore, the bond angles will not be same. Due to repulsion, bond angles will differ between them. Therefore, that statement is true. Now we'll see Roman number 3. Roman number 3. Boiling point of krypton is greater than xenon. Is that correct? False, right? Because both krypton and xenon will have London dispersion forces. And this London dispersion forces depends on their size. No? When size increases, London dispersion force increases. When size increases, when size increases, London dispersion force increases. When London dispersion force increases, bond strength increases. When bond strength increases, bond strength increases. When bond strength increases, boiling point or melting point will increase. Therefore, boiling point of, they have said, boiling point of krypton is greater than xenon. No, because the size of xenon is greater than krypton. Then boiling point of xenon should be greater than boiling point of krypton. They have said the boiling point of krypton is greater, therefore it's wrong. It's wrong. Roman number 3 done. Then Roman number 4. Stability of group 2 sulfates, solubility of group 2 sulfates decreases down the group primarily due to decrease in the hydration enthalpy of cations. You see here, what factors determine the solubility? Solubility depends on two things. What is it? Solubility depends on two things: hydration energy, hydration enthalpy, and then what's the next one? The bond dissociation enthalpy. Down the group, what will happen to both of this? This hydration enthalpy is a negative value. It is an exothermic process, and this is an endothermic process. It requires energy. This requires energy. This is an endothermic process. Okay. Therefore, down the group, what will happen to both of them? Down the group, both. Now let me take this hydration enthalpy just to make it simple to write it. And then the bond dissociation enthalpy as BE. Down the group, what will happen to hydration enthalpy and bond energy? Bond dissociation enthalpy. Both hydration enthalpy and BE, bond dissociation enthalpy, decreases. Both will decrease. Okay. Now, what they have said, solubility of group 2 sulfates decreases. No? Down the group, if solubility decreases means, then down the group, the positive value should increase. No? Down the group, the delta H of this solubility should be a positive value. For this to be a positive value, now delta H solubility is equal to delta H hydration enthalpy plus delta H bond dissociation enthalpy. Now you know delta H hydration enthalpy is a negative value, bond dissociation is a positive value. So this is how it is. Okay. So for this delta solubility, for it to be solubility, delta H should be negative. No? For delta H should be negative, delta HE should be greater than delta HBE, bond dissociation enthalpy. Hydration enthalpy should be greater than the bond dissociation enthalpy. But down the group, what will happen to both of these? Both will decrease. Hydration enthalpy and bond dissociation enthalpy will decrease. But as they have said, solubility decreases, then we can say then what can you say about the hydration enthalpy? Hydration enthalpy should be decrease further than the bond dissociation enthalpy. It should decrease more. It should down the group. This should decrease more than the bond dissociation enthalpy. Then only this positive will be greater. No? Then only this positive will be greater. Then delta H can be negative. Now the solubility depends on delta G. Delta G is equal to delta H minus T delta S. Here, delta S is a positive value. Delta S is positive. Minus T delta S is negative. Minus T delta S negative. So delta G depends on delta H. No? If delta H negative, if delta H is greater, if delta H is in positive wise, if it is greater, then delta H will be negative. In negative wise, if it become negative, then delta G is negative. Okay. If it is positive means the positive value should be greater than this minus T delta S value. Then the delta G will become positive. If delta G become positive, then it is not soluble. If delta G negative only, it is soluble. Here you see, therefore, down the group, what should have happened to this hydration enthalpy? Hydration enthalpy should be decreased further than the bond dissociation enthalpy. Then only down the group, the positive value will decrease, then the delta H will become positive. Therefore, they have said down the group, due to decrease in hydration enthalpy, yeah, it's correct. It's correct. Solubility of group 2 sulfates decreases down the group. They say it is decreasing. Why is it decreasing? Due to decrease in the hydration enthalpy. Both will decrease. Hydration enthalpy will decrease more than the bond dissociation enthalpy. That is the reason. Therefore, it's true. That's it. 2016, structure 1 done.